All right. Well, I think we're all present and accounted for. So let me go ahead and start. First, happy World Space Week, everybody. We're happy to be gathered here to help celebrate World Space Week. And this particular theme for this year is Women in Space. And so we're happy to celebrate all of the women that work in the aerospace industry and have been to space and work to support those folks on Earth. What we thought we'd do is put together a little bit of a Q&A today on our upcoming mission through NASA called the Flight Opportunities Program mission under SpaceWorks. That is part of our mission at SpaceWorks in bringing payloads, science returns, materials, experiments back from space down to the people of Earth. That's our long-term vision. I'm Dr. John Olds. I'm the Chief Executive Officer at SpaceWorks Enterprises. We are located in Atlanta, Georgia, and we're happy to be working with NASA on this upcoming mission to demonstrate some of our return capsule technologies. And along the way, we're happy to make space in our payload bay for some exciting and upcoming students as part of our STEM outreach activity. I'm here to answer questions later and help kind of orchestrate the meeting, but I wanted to turn it over now to let him introduce himself, our program manager for the overall project, and that's Tyler Kunze. Tyler is with me here in Atlanta, and Tyler manages the entire portfolio of all of our reentry capsules, including this particular mission. And I'll let Tyler introduce himself.
Thanks, John. So as John had mentioned, we are a company here trying to provide a small payload reentry capsule to bring products and experiments back from space. And that works in microgravity experiments or in-space manufacturing. That is the product line that I work on here. So I've been managing this portfolio for about 2 years now, and very excited with the support of NASA to be able to get a flight test under our belts here in the month of October. For this actual flight test and this project, we are taking a smaller version of our product line of capsules. This one is called the Red 4U. The Red 4U can deliver approximately 10 kilograms of payload back from space. And by the end of this project, we will have validated the final 100,000 feet of reentry for this Red 4U capsule. And this 100,000 feet reentry condition will be the same as when we bring it back from low Earth orbit, hopefully in the next year or so. So at this point, I'm going to show the concept of operations for this mission. Can everyone see that?
Yes.
Okay. So this is the mission that we have set out in front of us for October 19th. In order to get to 100,000 feet, we are working with Near Space Corporations, which is based out in Oregon, and they have developed a high altitude balloon for us to fly underneath. So as you can see in the bottom left here, this is that high altitude balloon, and we will be connected as a capsule underneath. We will float up at about 1,000 feet per minute. Take an hour or so to get up to 100,000 feet. We'll then get there, float for a bit to get to the optimal drop location, and then we will release the red capsule at that 100,000 foot condition. Shortly after release from the high altitude balloon, we will deploy a decelerator parachute. We call this a Drogue Parachute. This will happen at less than Mach 1 at about 25,000, 30,000 feet above the ground. After we're stabilized under this Drogue Parachute, we will deploy a parafoil at 20,000 feet. And this is one of the major things that we're testing under this experiment. This is a guided parafoil system, and it is all autonomous. So we will give a target location on the ground prior to drop, and then the parachute will do everything else to get our capsule exactly down to that location. Yeah, so we will deploy that parafoil at 20,000 feet, and it will do everything on its own to get down to this target location right here on the ground. And we will set that prior to launch, and the parafoil will take it from there at 20,000 feet. So that is the main goal that we are trying to validate as part of this experiment. We have previously tested that parafoil from about 8,000 feet. So going up to 100,000 feet is a major climb and a major technical hurdle that we'll have to overcome here. In addition to testing the parafoil, we're also validating our communications and sensors in suborbital environments. And of course, we are providing a platform for several student experiments that we're happy to test here. And so as a quick transition before we open up to some Q&A, I wanted to show some of those pictures of the student payloads as they are integrated. So I will start with this picture here. So this is the final integrated version of the student payloads that we'll be happy to talk about a little bit here and have a lot of questions about how we came up with these cool concepts. But this is how they were assembled prior to putting them into the capsule. And then right here, this picture is what the final version of them look like inside our capsule. So as you can see, this is a flight-ready capsule with a lot of different harnessing, different critical components going on there. And then smack dab in the middle of our payload bay is where we have these experiments that we are very excited to talk more about. So at this point, Janet, I wanted to kick it over to you if you wanted to start us off and talk a little bit about the student experiments and kind of, I guess, give the students really a chance here to talk about how they came up with such great concepts.
I'm going to throw these questions to you. The first one is, you guys, do you want to kind of tell everybody what the experiment is? Why don't we start there? Somebody, either one of you, say what you are kind of going to send up as your experiment.
So basically, what we're going to do is we're sending up a thermoluminescent dosimeter up into 100,000 feet into the air, and then we have 2 on the ground, and we want to see the radiation reading difference between the 2 to find out how effective the atmosphere is at blocking the radiation and how much radiation you'll receive depending on where you are.
And what do you, I mean, you guys, what do you think, or what might this experiment indicate when it comes to how effective Earth's atmosphere is? I mean, what are you guys proposing? What's your hypothesis here?
Well, what we really want to see is if the radiation that is, well, up there, if it's higher than if it's down here. And our hypothesis is if the thermoluminescent dosimeter that traveled in the weather balloon experienced 2 times more radiation than the TLDs on the surface of the Earth, then the atmosphere blocks 50% of the radiation from entering the Earth.
Now, why did you guys choose that number? Was that you thought as a scientist that's a good number? How did you go about choosing that particular number?
We just used it as like an example, and depending on if that number changes, we'll know how effective it is.
All right, Brian and Shawn, why don't you tell us the name of your experiment?
So we are doing seeds. We are going to send up squash and pea seeds.
Here's also,
And yeah,
this
these
is
we found these
vial of,
vials. And we made a 3D printed case for these vials so that we don't break the seed, because that would impact the results as it possibly shakes. Well, we want to see how quickly it germinates, how much crop it yields, and inside of the fruits it has, if any. Then we want to see how many seeds each of those have and how viable those seeds are. And we're planning to chart the dependent and independent variables on a data chart. My research has led me to believe that the seeds will probably grow slower after going to space. We're going to test that to add to the data set. For us, peas and squash have an exceptionally high germination rate, so we're going to be able to test the difference to see whether it went slower, faster, or something else happened to it from the space trip.
You guys are on exciting paths in your education and your careers. You are the next generation of aerospace professionals, whether you be space lawyers or aerospace engineers or astronauts. We want you to join us. And so it's fantastic to be working with you on this flight. You have some great scientific experiments that you're exploring. You're getting involved in space flight or near space flight at a young age. And I want to thank Janet for introducing our company to you, and also Shawn Case for introducing us to Janet. So we're excited about this, and we're really pumped. Looking forward to flying with you on October 19th, weather permitting. You know, that's the scheduled date. We'll go up and down and see what it looks like up there, get some great pictures give you a free fall on the way down and then a gentle glide down to the touchdown and get your experiments back, and you can start doing the rest of your science. So congratulations, pleasure to be working with you all. And thanks for the update today. I'm really fascinated. You all are on top of it. You're smart, you know your experiments, and you speak well. And I'm glad to have met all of you.
Thank you all so much for this opportunity.
Thank you.
Thank you so much for your time, and
you,
thank you for
everybody.
listening.
Thank
It's
you.
an honor to fly with you, and
Thank you so much for this opportunity, and this was a great experience and really opened new doors.
As the best socially distanced handshake that we now have, everybody live long and prosper. We will see your experiments in space